Alright, let's get back to doing more of the planning for the slides here. I've been away. I had to do some stuff for the house, and because of that, I'm going to try to do 3 chapters tonight. So a little bit of makeup for this. So let's go for it. This chapter 3 is on of the prerequisites is on polynomials and special products. So the most common type of algebraic expression is called the polynomial, from poly, many, and nomial translates kind of into terms. So examples of polynomials are like, let me try to draw bigger, 2x plus 5, 3x to the 4 minus 7x squared plus 2x plus 4. You can see, as we've said before, that each one of those, anything separated by addition and or subtraction, is called term. And because there are 4 terms, this is a polynomial. If there's more than one term, it's considered a polynomial. So you wouldn't call like x squared a polynomial. That's only a nomial, a mononomial, I guess. So those are some examples. The first two, well, there was a third example that it gave, which was 5x squared y squared minus xy plus 3. You can see we have 2 letters in this term, so the book was saying that the first 2 that I wrote were polynomials in x. The one I just erased was a polynomial in x and y. So there can be polynomials in multiple different terms, the terms being variables, I guess, multiple variable polynomials. The terms of a polynomial in x have the form ax to the k, where a is the coefficient, as I believe we've explained before, but k is the degree of the term. That's what it's called. For instance, a third degree polynomial would be something like 2x to the 3 minus 5x squared plus 1. And if we looked at the terms and degrees of the polynomial, you'd see 2x to the 3 plus negative 5x to the 2 plus 0x plus 1. And so we can write those coefficients as 2 minus 5, 0, and 1. So the definition of a polynomial, which we'll write out in its completeness, let a0, a1, a2, to whatever a that you end up having, be real numbers and let n be a non-negative integer. Obviously, we must be counting up, so n cannot be negative. A polynomial that's only to highlight that it's a term that we should remember, is an expression of the form a n x to the n plus a n minus 1 x to the n minus 1 plus all the way down to a1 x plus a0, where a n is not equal to 0. So we're saying that the first term can't be 0. Any other term can. It's only an cannot be, because we are then going to say that the polynomial is of degree n. An is the leading coefficient and A0 is the constant term. So what that says is an can't be 0. Let's use a different color. Use red. An can't be 0, because if an is 0, then that term doesn't exist. We can write it. We don't have to write it, which means that it can't. The polynomial cannot be of degree n if the first term doesn't exist. So that term must exist. Any other term, an minus 1, a6, a1 can be 0. Even a0 can be 0. An is called the leading coefficient, and a0 is a constant term. It's a constant term because there is no x factor at the end of it. It's x to the 0. You could say that this is x to the 1 and this is x to the 0. But remember that x to the 0 is 1, and x to the 1 is just x. So we can write it like this, and it's the same thing. Alright? In standard form, a polynomial is written with descending powers of x. So while you could write the x, 2x plus x squared minus x to the 3, you don't normally see polynomials that way. That is a weird way to see it, because we write it descending powers of x, not ascending powers of x. Now, you will see in certain times descending powers of x and ascending powers of something else. Maybe sometimes you won't. Some books don't do it that way. So you can see x squared y squared plus xy plus 6. Well, sometimes you'll see x like 6x squared plus 2xy plus y squared, where the powers of y go up even though the powers of x go down. That you may see, but when it's a polynomial of a single variable, you usually see only descending powers. In fact, that's the standard. So there's some dumb examples we'll go over real quick. So it says here's a polynomial 4x squared minus 5x the 7 minus 2 plus 3x. Rewrite that in the standard form. Well, that's easy. The 7 is the highest one, so it's minus 5x to the 7 plus 4x squared. This x at the end shouldn't be there. Plus 3x minus 2. That's the standard form. And what degree is this? This is 7th degree, because the highest one is the 7. There's some other dumb examples that we don't have to go over. It does have one that might be beneficial. Apparently they are calling a single term a polynomial. What's the standard form? Well, the standard form is just 8, because that's 8x to the 0. And the degree of this polynomial is 0. But it's a constant, so we normally don't consider that a polynomial. A polynomial that has all 0 coefficients is called the 0 polynomial, and it is denoted by a 0. No degree is assigned to this particular polynomial. Expressions such as the square root of x squared minus 3 and x squared plus 5x to the negative 1 are not polynomials. So just for visual, let's write that. Those are not polynomials. it says, note, for polynomials in more than one variable, the degree of a term is the sum of the exponents of the variables in the term. The degree of the polynomial is the highest degree of its terms. So, for example, we'll do a simple one. X to the 4, y to the 3, plus x to the 3, y to the 3, plus 2xy plus 6, for example, just cut out a bunch of the middle ones, has a degree of 7 because x to the 4, y to the 3 gives us 4th degree plus 3rd degree, 7th degree. That is the degree of the polynomial. You can add and subtract polynomials much the same way as you add and subtract real numbers. Simply add or subtract the like terms having the same variables and same powers, by adding their coefficients. For instance, negative 3xy squared, oops, I'm writing an erase there. And 5xy squared are like terms, so you can add them to get a result of 2xy squared. Some people find it easier to write these in very long form. So the first example, example 2, the other example we didn't number, is to take 5x cubed minus 7x squared minus 3 and add that to x cubed plus 2x squared minus x plus 8. So I'm going to do the first one kind of in the head, and then we'll do the second one the way that a lot of people like to show them. In fact, that's example 3. So let's do both of these in the head then. Okay, so 5x cubed. Now remember, if this is a minus, then it distributes to the rest of them, but we have a plus, so we don't have to worry about that right now. So 5x cubed plus x cubed is 6x cubed. Minus 7x squared plus 2x squared is minus 5x squared. There is no x term, so it's 0x minus x. And then you have minus 3 plus 8. And the answer is 6x cubed minus 5x squared minus x plus 5, which is what the book has. The next one it gives is 7x to the 4 minus x squared minus x to the 4 plus 2 minus exactly what we said to look out for, minus 4x squared plus 3x. This is the same as, the first term remains the same. And then we're going to distribute the negative sign. So minus 3x to the 4 plus 4x squared minus 3x. Remember that all signs flip when you distribute the negative sign. So let's do that in our heads. 7 minus 3 is 4x to the 4. Minus 1 plus 4 is going to be plus 3x squared. You'll notice that there was not a cubed term in either of those. Actually, I'm going to show you how they're grouping this. They're not doing it in the head. They're doing this step first. And they're saying, let's group the terms. Essentially what I'm saying out loud, they're doing on paper here. So they put 7 and minus 3. And then they've grouped those terms by factoring out the x4. Then you have a plus minus 1 plus 4 x squared plus minus 4 minus 3 x plus 2, and the second one is plus 0, so we're not going to write that. And that's the same as we had before, 4x to the 4 plus 3x squared plus negative 7, or you could just write minus 7. x plus 2. A common mistake is to fail to change the sign of each term inside the parentheses preceded by a negative sign, which we just went over. You distribute, you change all the terms. So they have this minus x squared minus x plus 3, and they're saying that that is equal to minus x squared plus x minus 3, and it is not equal to minus x squared minus x plus 3. And you can see here, they took that minus and they distributed it here, but they did not distribute the minus to the second term. They do it here, they do not do it here. So be careful. That is a big problem that a lot of students run into, even well into calculus. Just something to look out for. To find the product of two polynomials, use the left and right distributive properties. For example, if you treat 5 plus 7, and this is something some of you may be familiar with. For example, 5x plus 7, if you treat that as a single quantity, you can multiply 3x minus 2 by it as follows. If we take the first two terms and multiply them, then you get 5x times 3x. Then if you take the outer two terms, you're distributing the 5x to the first one, and then you're distributing the 5x to the second one. Then you get, in fact, let's just do this by colors. Okay. So if I take the blue, 5x and 3x, then I get 5x times 3x. If I take the red and I get 5x times 2, it's always plus 5x times, and if you'll notice, it's a negative 2. And then let's do green. We want the product of the 7 times the first one, so plus 7 times 3x, and then we want the product of, back to black, the second of the first one and the second of the second one, plus 7 times 2. Now, if you look at the colors and how they correspond to the distribution here, the blue one is the first two terms, the red one is the outer two terms, the green one is the inner two terms, and the black one is the last two terms. The last term of the first one, the last term of the second one. So we call this method the FOIL method, for first, outer, inner, last. And that's how you remember to distribute it. So let's go through and see what we have here. We have a 5x times 3x is going to be 5 times 3, 15. X times x, x squared, plus 5 times a negative 2, negative 10x times 1. And then we have plus 7 times 3, 21, plus, or times x times 1, which is x, plus 7 times 2, which is 14. You'll notice that with the FOIL method, with polynomials of that degree, of first degree polynomial twice multiplied by a first degree polynomial times a first degree polynomial, will result in two inner terms that are both in x. So you can add those together and simplify further. You have 15x squared plus 21 minus 10 plus 11x plus 14. And that's the answer to that. FOIL is going to be extremely useful because there's a lot of times that you're going to need to multiply those two things. When multiplying polynomials, be sure to multiply each term of one polynomial by each term of the other. So I said there was a different way to add, so you know what, we're going to do two things. So the next example says multiply x squared minus 2x plus 2 by x squared plus 2x plus 2. So you have, this is a plus, this is a minus. That's the only difference between the two. But we're also, for the last one, going to add those two together. So let's go back one and add x squared minus 2x plus 2. And instead of writing it the way we did before, we're going to write it vertically. So we're going to say plus x squared plus 2x plus 2. And from here it gets easy. So plus 2 is plus 4. Minus 2 plus 2 is plus 0x. And plus 1 is going to be 2x squared. And so the answer is going to be 2x squared plus 4. But you can use this vertical way of writing it to add up things pretty easy. They're doing it for multiplication. So now let's use a vertical arrangement for multiplication. So we have these two guys, x squared minus 2x plus 2 times x squared plus 2x plus 2. Okay, so very similar to how we do multiplication of regular numbers, except we're going to do it kind of backwards, because instead of multiplying by the lowest one first, we're going to multiply by the highest one first. So similar to FOIL, we're going to distribute this guy. Remember, F was red, so, or F was blue, I guess. So we're going to take him and multiply across all three. So x squared times x squared is going to be x to the 4th, minus 2x times x squared plus 2 times x squared. So we just took the x squared and multiplied it all the way through. That's what we were going to do, but we're going to skip that step and just write it as if we already did it. So we're going to start with the first term, which is x to the 4 minus 2x cubed plus 2x squared. And then we are going to do the inner one, which we're going to call green. And we're going to say the 2x distributed across all three. So we're going to have 2x times x squared. That's going to be 2x cubed. 2x times negative 2x is going to be minus 4x squared. And then 2x times 2 is going to be plus 4x. And then we're going to do the last one, which is going to be back to black. The red was the outer, but it's not, doesn't work exactly the same way. Don't associate it with FOIL. FOIL is only good for the degree 1 polynomial multiplied by degree 1, but this is just so that you keep these straight here. So you have 2 times x squared, which is plus 2x squared, 2 times negative 2x, which is going to be minus 4x, and 2 times 2, which is going to be plus 4. So this, using what we had before in the addition, makes it very easy to add everything up. So you have x to the 4, this positive 2, and this positive 2 and this minus 2 are going to cancel each other out. So you have 0, x3. We have plus 2 minus 4 plus 2, so we have plus 0 x squared. Then we have plus 4x minus 4x plus 0x plus 4. And you get a very simple and beautiful x to the 4th plus 4 once you combine like terms. And that's the answer to this multiplication. Alright. So there are some special products knowing of what we just saw here, and we actually used one in the previous chapter. So these special products are as follows. When you have u plus v times u minus v, if we multiply it out, if we FOIL it out, we have u squared if you really think of it, we're multiplying that first u by this u by this u, and then this u by the v, so we have uv, sorry, uv. Then we have the v times u. I'm sorry, I messed that up. Ignore what I said there. Okay, you have plus u times a negative v, which is the second term of the second polynomial. Then we have plus vu, because we're multiplying this v times this u. And then we have minus v squared, because you have minus v times a positive v, which ends up being v squared, but we still have to take the negative sign into account, so it ends up to be minus v, which means that you get u squared. These two terms cancel out, minus uv and plus vu, which remember you can switch those around, so it's uv, minus v squared. And we call this a difference of squares. And note that while when you see this, it's going to result in this, the more important result is when you see this, it actually results in that as its factorization. We'll talk about that more later, but the equal sign means you can go both ways. So I would argue that knowing that this is a difference of squares, its factorization into the two polynomials that create it is more important than going from the polynomials to the difference of squares. It says square of a binomial. Binomial is another term for first degree polynomial because there's two terms binomial. So you have u plus v squared and u minus v squared. That's the same thing as u plus v times u plus v, or u minus v times u minus v. Those do not result in beautiful, elegant things like the difference of squares. It's actually going to be u squared. Remember, u times u. If we think it out, u, let's do the laser pointer here, u times u plus v times u plus v times u, I'm sorry, u times u plus u times v plus v times u plus v times v. So you get u squared plus uv plus vu plus v squared, or u squared plus 2uv plus v squared. And this is what I was saying, where the terms decrease for the u term, but they increase for the v term, the second variable. Now u and v are going to be x and a number, or x and y, or two numbers. If you don't know what they are, that's one way to factor it out. But it will always result in that form. Similar on the negative side, it doesn't cancel out like the difference of squares. You just get u squared minus uv minus vu plus v squared, and that's going to be u squared minus 2uv plus v squared. And why does it end up with a plus v squared at the end? Well, you have a minus v times a minus v. The negative signs multiply and cancel each other out to be a positive 1, and then the v's end up being v squared. So even though it's the binomial is a minus v, you still end up with a positive v squared term. And then you have the cube of a binomial. Where you have u plus v, looks like a v, cubed, or u minus v cubed. We can take advantage of the fact that we already know what the square of a binomial is, so this actually ends up being u plus v times the thing we just wrote down, u squared plus 2uv plus v. This is u minus v times u squared plus, or minus, sorry, minus 2uv plus v squared. And now we can do similar to FOIL we're going to distribute the u through all those, so that's u cubed plus 2u squared v plus uv squared. And then you distribute the v through all of them, plus u squared v plus 2uv squared plus v cubed. Similarly, you have down here u cubed minus 2u squared v plus uv squared minus u squared v plus 2uv squared minus v cubed. And these two terms will add up or subtract. So you have u cubed plus 3u squared v, or u cubed minus 3u squared v. And then these terms, uv squared and uv squared, will add up. So you get, in both cases, plus 3uv squared plus 3uv squared. And then the last term switches signs, so you have plus v cubed minus v cubed. And those correspond to those equations. If you keep doing this, I don't know if they talk about it, but if you keep doing this, you can use Pascal's triangle. That's just a little trick. And you can get the coefficients of the square. This would be the square, this would be the cube, this would be the to the fourth of each of the polynomials. Now, that doesn't give you the sign. You'll have to work that one out for yourself, but these will at least be the coefficients. So you can hear it's 1, 3, 3, 1. That corresponds to this row of Pascal's triangle. That's just a little quirk. They do not talk about it in the book. At this point, they may talk about it later, who knows. Okay, so there's some examples. I'm not going to go through them because you have the formula right here. If you don't understand how it works, go ahead and expand it out, do the work, and prove to yourself that it works. If you understand this well enough, I would not blame you if you just plug in the formula and say, okay, I know that when this is x and this is 3, I'm going to put it into this formula and it's going to pop out the right answer. However, there is an example that we will go through before we move on. And that is a practical application of this, the volume of a box. So it says, an open box is made by cutting squares out of the corner of a piece of metal that is 16 inches by 20 inches, as shown in this figure. So you have 16 inches by 20 inches. And you're going to cut out some square on the side. And when you do that, then you will fold those sides up to make the box, and you'll get something that looks like this. And the nice thing about this guy is that this length here, or this length here, we can call that A, and we'll call it red A, is going to be equal to 20 minus 2x, and you can see that because this length is 20, this length of this little square is x, so there's an x there, there's an x there, 20, you got x, you got whatever 20 minus x is, and then you've got another x, so it's 20 minus 2x. Similarly, you have 16 minus 2x here for the length of this side. We're going to call it b. And so, what if I wanted to find the volume of this box? Well, right away, I know that the volume of the box is going to be the height. Come here. The height times the length times the width, which the height is going to be x. This is going to be x times a times b, which we can substitute as x, 20 minus 2x, and 16 minus 2x. So how would we get all that out? Well, we can plug and chug, as they used to say. So let's FOIL the first one. You get 20 times 16 is going to be 320. 20 times minus 2x is going to be minus 40x. And then minus 2x times 16 is going to be minus 32x. And then minus 2 times minus 2 is going to be plus 4x squared. That's not the right way to write it, but we're just doing the FOIL right now. And then there's multiplied by x at the end. So now let's flip it as we do this math. X times 4x squared is going to be 4x cubed. X, well, we didn't do the add, but this is going to be minus 72x. So x times that is going to be minus 72x squared. Then we have plus 320x. So that is your formula for the volume of a box with this configuration. So if x was, say, 1 inch, if you were only going to cut little 1-inch squares off of the side, you could plug x in. That's where the plug and chug comes from. 4 times 1 to the 3 minus 72 times 1 squared plus 320 times 1. That's going to be 252 inches cubed. So let's say we bump up x to 2. Now you have 4, 2 to the 3 minus 72 times 2 squared plus 320 times 2. That's going to be the same as 4 times 8 minus 72 times 4 plus 320 times 2. And that's going to be 384 cubic inches. If we bump it up to 3, that'll be 420, and there is actually a point at which the volume will be maximum. You can work that one out on your own. I will work that out in the slides. But remember how we solve it here, because that will become important in calculus later. And that is essentially chapter 3. So now, I mean, that took 1 page. That's great. So let's move on to chapter 4 now. Section 4 of chapter P, prerequisites. Keep saying chapter. Then we talk about factoring. So I told you factoring was going to become important, and we're there. So the process of writing a polynomial as a product is called factoring. So that means, what that means in English is taking a polynomial and writing it down as smaller polynomials that are a product to make that polynomial, or binomials or whatever that end up being multiplied together to make that polynomial, is called factoring. So it's an important tool for solving equations and for reducing fractional expressions. Unless noted otherwise, when you are asked to factor a polynomial, you can assume that you are hunting for factors with integer coefficients. If a polynomial cannot be factored using integer coefficients, then it is prime or irreducible over the integers. So we're going to write that, prime or irreducible over the integers. The whole term is one term. For instance, the polynomial x squared minus 3 is irreducible over the integers. Over the real numbers, this polynomial can be factored as a difference of squares. But 3 isn't a square, right? Because it's not an integer square. It's not a complete square. So you have x squared minus 3 is the same as x plus the square root of 3 times x minus the square root of 3. And the reason we would factor it that way is because we want the lowest term in the variable as possible. And here it's first degree in x. A polynomial is completely factored when each of its factors is prime. For example, let's get big. X to the 3 minus x squared plus x to the 4 minus 4 is prime when it is at x minus 1 times x squared plus 4. The x squared plus 4 cannot be factored down any further, and the x minus 1 can't, but the x squared plus 4 is a little bit deceiving. We know that x squared minus 4 can be factored into the nice x plus 2, x minus 2, but x squared plus 4 cannot be. That plus throws a wrench in what we're trying to do here. So, and it says it. That is completely factored, however, this one is not. I'm sorry, minus. Why? Because we have x minus 1, and then you have x squared minus 4, which means we can then factor that further. That's the complete factorization there. Now, there can be repeated factors, just like in the factorization of an integer. But what we're looking for here, the simplest type of factoring involves a polynomial that can be written as a product of a monomial and another polynomial. Technique used here is the distributive property, where we have a times b plus c is equal to ab plus ac. In the reverse direction, when you have this, you're trying to get back to that. That's the simplest factoring. So let's look at an example there. It's called a common factor. So example 1 of p dot 4 is removing the common factors. So we have 6x cubed minus 4x. Well, that's simple. Each term has at least one x in it, and each term is even. So let me try pulling out a 2 from each of those. So 6 divided by 2 is 3, and 4 divided by 2 is 2. So I know I can pull out a 2 from there. X cubed divided by x is x squared, sorry. And then x divided by x is 1, so I'm going to leave that one blank. We know this is a minus sign between them. And we've pulled out 2x. So each term had an x, each term had a 2. We were able to factor that out of the binomial there. Dang. And so we end up with a factorization of 2x times 3x squared minus 2. And that is complete. Very simple there. But you'll hear me, at least, and probably others, say pulling it out. We pulled out, damn it. We pulled out a 2x from here, because you pulled out a 2x from this guy, and you pulled out a 2x from that guy. It's the same as dividing out or factoring out. Those things all mean the same thing. So let's look at part B. We have x minus 2 times 2x plus x minus 2 times 3. Very simple. let's say you did some other factorization work and this is what you got for each of those terms. Very simple. You can see that x minus 2 is common to both of them. So you can say x minus 2 is pulled out of the first one. What's left is 2x plus 3. Oh, and look at that. You have another binomial in that. It looks a little weird in the first part, but in the second one, that's what you get. It's because in the first part, it wasn't simplified down to the third degree polynomial or the second degree polynomial that you would have gotten. So it looks different, but it results in the same thing, a multiplication of binomials. So what if you want to factor a special polynomial? Well, they're just showing the reverse of what we showed in the special products. So factoring special polynomial forms. You have u squared minus v squared equals u plus v times u minus v. Same thing. What if a perfect square trinomial? U squared plus 2uv plus v squared, or u squared minus 2uv plus v squared. That's going to factor to, guess what? U plus v squared and u minus v squared. Alright, and then we have sum or difference of two cubes. That's going to be u cubed plus v cubed. That's a v. And u cubed minus v cubed. And that's going to be, you can take out a u plus v or a u minus v, and then u squared minus uv plus v squared, or u squared plus uv minus plus v squared. Same thing as the special products, just in reverse. One of the easiest special polynomial forms to factor is the difference of squares. You get this. Ooh. And again, we said it's very important. That's one of the ones you'll use the most. It says to recognize perfect square terms, look for the coefficients that are squares of integers and variables raised to even powers. So when you have, in example 2, let's look at example 2. Removing a common factor first. I'm not too concerned with the handwriting there because what's more important is the math. These are examples. These will be redone in the slides anyway. 3 minus 12x squared is equal to 3, 1 minus 4x squared, and that's equal to, so look, we took out a 3 first, and then what do you notice about this guy here? Well, that's a difference of squares. So 1 squared is 1, and 2x is the square root of that one. So 2x times 2x is going to give you 4x squared. So we know that's a difference of squares. We can factor that as such. You can see it's written backwards because normally the higher degree goes first. So we have 3 times 1 plus 2x times 1 minus 2x. And those are the two factors. To write it more correctly, 2x plus 1 minus 2x plus 1. There you go. That's the factorization of that. So you have to check for common factors, pull those out, then look for difference of squares or some other special form like the cubes or something like that. So let's look at example 3. Factoring the difference of two squares. So you have x plus 2 squared minus y squared. It looks weird and hard because there's multiple terms in the first term, which is x plus 2 squared, but it is a square. Obviously there's a square minus a square, so you can do the same thing. You just have to remember that normally where you say u plus v and u minus v, in this case your u is the x plus 2. So it's u minus plus v, and yes, I know that's a y. It's because that's the v in our term here, times u minus v. And so that's the factorization. To write it more correctly, you want to write the variables before the constant. Okay, and then we have, that was a 16x to the 4 minus 81. 81 is a perfect square, 16 is a perfect square, x to the 4th is a perfect square, so we have 4x squared minus 9 times 4x squared plus 9. It doesn't matter if you write the plus 9 first or the minus 9 first, because it's multiplication, you can write them either way. Because it's a difference of squares, I sometimes slip up and I write the difference first, but that's the correct factorization. Now, if you'll notice, we have another difference of squares. So the square of that one is 2x plus 3 and 2x minus 3. Remember that the sum of squares is not its prime. So you have 4x plus 9. You cannot factor that one further. If it was 4x plus 16, you could factor out a 4, but any sum of squares that has nothing in common, you cannot factor out any further. So that is the factorization there. A perfect square trinomial is the square of a binomial, and it has the following form. It's the same thing that we wrote over here. This is why it's called a perfect square trinomial, because it is the square of a binomial. Note that the first and last terms are squares, and the middle term is twice the product of u and v. So we could factor that out too. It's just working with the formula. Let's move on to the next one. So trinomials with binomial factors. Alright. To factor a trinomial of the form ax squared plus bx plus c, use the following pattern. That ax squared plus bx plus c is going to be equal to some FOILed pair of binomials. So you have and I don't know what they are, but there's going to be something here and something there and something here and something there. And we know they're both going to be plus because the coefficients themselves could be negative. So we're going to write a plus, and this is going to be something x, and this is going to be something x. And these are going to be the factors of a, and these are going to be the factors of c. So the goal is to find a combination of factors of a and c so that the outer and inner products add up to the middle term bx. For instance, in the trinomial 6x squared plus 17x plus 5, you can write that, well, they skip right to it. 2x plus 5 times 3x plus 1 is going to give you a FOIL of 6x squared plus 2x plus 15x plus 6 plus 5, I'm sorry. And these two will add up to 17x. So that's what you're looking for. And when I was a kid and I tried to solve these, I would always look at what factors of, normally this one does not have a coefficient. You try to reduce it down to the terms itself. So I always looked for what factors of this would add up to that number. When there's a coefficient, a leading coefficient, then yeah, you have to take that into account. So let's look at the first example, which is this is example 7. It says the leading coefficient is 1, which is exactly what we're talking about. So you have x squared minus 7x plus 12. So if we look at the factors of 12, what makes up 12? Well, 12 times 1 is 12. 2 times 6 is 12. 6 times 2, same thing. You have 3 times 4 is 12. And then they all reverse. 4 times 3, 6 times 2, and 1 times 12. Yeah, I wrote them reverse, but whatever. It just means that you don't have to go through the second part of the list. Well, I look at 3 and 4, and I see that 3 plus 4 is going to give me 7. So that's how, when I was a kid, that's how I would solve them. X squared minus 7x plus 12 is going to be equal to x minus 3 times x minus 4. And the reason that I look at it that way is because the 7 is negative, right? And so negative 3 plus negative 4 is going to get me to negative 7, and that's what I'm looking for. So that's exactly the way they do it, is actually write out x. The possible factorizations are x minus 2 times x minus 6, x minus 1 times x minus 12, which is exactly what I was doing, just a little bit differently in the mind. X minus 3 times x minus 4. And that will get you to that. The thing of that, testing the middle term, you'll find that the correct factorization is x minus 3 times x minus 4, because that's the only one that gets you to negative 7 as the middle term. And let's do the FOIL so that I can prove to you that that's how it works, because I just did this little minus 7 part here. Okay, so then you get, if we take this and we FOIL it out, you get x times x, x times minus 3, or x times minus 4, sorry, x times minus 3, and negative 4 times negative 3, which is positive 12. So then that adds up to minus 7x plus 12, which is what we were looking for. Yeah, I realized that I didn't write the one there. Okay, so now they go to the next example, example 8, where the leading factor is not 1. So, using their method, you can list out all the possible factors of A and C. So you have 2, they're all going to be 2x, because the only factor of 2 is 2. So you have 2x, and then 15 factors into, so let's look at 2 times 1 for A, that's it. 15 is 15 and 1. 5 and 3, and that's it. So you have multiple ways that can be arranged. 2x minus 1 times x plus 15. remember that you're looking for a negative 15. So the only possible combinations of signs have to be that the signs are flipped. You cannot have 2x plus 1 times x plus 15, because 15 times 1 is indeed 1, but it's not negative 15. I'm sorry. 15 times 1 is indeed 15, but it's not negative 15, because you need to get to a negative 15. So they can't both be negative and they can't both be positive. They have to be flipped like they are here. So we can't write that. So the next term would be 2x minus 3, x plus 5, 2x minus 5, x plus 3, and 2x minus 15, x plus 1. And then the second set of possible coefficients are the same, except the negative and the positive are flipped. So 2x plus 1, x minus 15, blah, 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 blah. Just write them out real quick. Okay, and if we look, there should only be one set of polynomials here, binomials, that gets us to a positive x in the middle, and that looks to be this guy here. Because the 2x times x would be 2x squared. You got the minus 5, or the 2x times the 3. You got plus 6x, minus 5 times x, plus, well, minus 15. And the middle term here, plus 6 minus 5 is going to get you plus 1. So you get 2x squared plus x minus 15. And that gives us what we're looking for, so we know that that's the correct factorization. And then sometimes you can factor it by grouping them. So let's look at example 9. So if you have x cubed minus 2x squared minus 3x plus 6, if you group them, you might be able to get something. So if we look at the first terms, we're going to take that one, but we're going to group x cubed minus 2x squared. I can take an x squared out of that one. And if I look at the second set, we have minus, and look what I'm about to do here, minus 3x minus 6, because I factored out a negative, but this was positive, so I have to switch that sign. Always remember to switch the signs. So here, you can factor out a 3, and you're left with x minus 2. Whoa, look at that. We've got an x minus 2 and x minus 2. So we're going to factor that out and leave us with x squared minus 3. And that's the factorization. So you can group terms strategically to somehow wind up with binomials, if you can see that. Doing the same thing with higher order terms can be very tough. So as soon as you get to even quads or trinomials, you can see that there's some weird stuff you have to do. And this is where it can get tricky. And I know we talked about tricks you can do in previous sections. This is exactly what we're going to use all the properties that we came up with in P.1 to do the factorization here. So if we look at 2x squared plus 5x minus 3, that you could do the factorization and write out all the stuff that we just wrote out. but there could be an easier way. And the easier way is to realize that 5x is actually the sum of 6x and a minus x. And by writing it creatively that way, then we can start to do grouping. So if I say that that is the same as this, and then I group these two as a minus x plus 3, and I group these two as a 2x squared plus 6x, and I factor out of this guy a 2x, then you'll see that I have x plus 3 in two places, and I can factor that out, x plus 3, and get 2x minus 1 times x plus 3. And that is the factorization. It took some creative grouping, but we got it to work. And that closes out this section. There's no special thing like the box on this one. Okay, so let's move on to P.5. And, come on. Again, I'm going to be making slides of this, and those are going to be their own videos. They're going to be a lot more informative, and we're going to go through all the exercises. One of these live streams is probably going to be me fumbling through Manim or some other animation package, so that those factoring things out and moving things from one side to the other is going to become very visual, and it should make a lot more sense in those than me trying to do it on a notepad here. That's my goal. And again, if you have questions, or if you think that something could be explained better, or you can help me do Manim or some other animation of this stuff, let me know. I am always in the mood to accept help. Okay, so fractional expressions. Okay, so things are going to get a little bit more difficult, but not too difficult, because we're still in the prerequisites. And algebra, although for some of you may not feel this way, is going to be the simplest of the subjects we're going to tackle on this channel. Here we go. Fractions. So the domain of an algebraic expression, the set of real numbers for which an algebraic expression is defined, is called the domain of the expression. So domain. That is going to be the set of real numbers over which an expression I guess it's an A, is defined. Two algebraic expressions are equivalent if they have the same domain and yield the same values for all numbers in their domain. For example, just as we saw in the last section, x plus 1 plus x plus 2 is equivalent to 2x plus 3, because for all x, they will yield the same answer. So let's find the domain of an algebraic expression. The domain of the polynomial 2x cubed plus 3x plus 4 is the set of all real numbers. That's how you write the set of all real numbers. In fact, the domain of any polynomial is the set of all real numbers unless the domain is specifically restricted. And if we're going to use, that's disgusting. if we're going to use set notation, the set of all real numbers. Usually the R itself can also function as the set of all real numbers, but I like to include the brackets so that it is explicit that I'm talking about a set. If you look at, although we dealt with polynomials and a lot of algebra will deal with polynomials, algebra is not all polynomials. So the domain of the radical expression x minus 2 is the set of all real numbers greater than or equal to 2, because the square root of a negative number is not a real number. So you know, as long as x minus 2 is greater than or equal to 0, then this expression works. Otherwise, it's not a real number. The result is not a real number. That's why I didn't put the set notation. So if it doesn't result in a real number, then it restricts the domain of that expression. The domain of the expression, and this is a nice little interesting one, x plus 2 divided by x minus 3 is all real numbers except 3. Why? Because the bottom, the denominator of that expression, will equal 0, and anything divided by 0 is undefined. So that result is not a real number, and thus that one point is not part of the domain of that expression. The quotient of two algebraic expressions is called a fractional expression, just like the one we saw right now. Moreover, the quotient of two polynomials, such as 1 over x, so we have let's define it. The quotient of two polynomials is called a rational expression. Remember, like we said in P.1, the reason that we use the term rational is because it is a ratio of two polynomials. Recall that a fraction is in reduced form if its numerator and denominator have no factors in common aside from 1 or negative 1. To write a fraction in reduced form, apply the following rule. A times c over b times c is the same thing as a divided by b, where b not equal to 0 and c not equal to 0. The key to success in simplifying rational expression lies in your ability to factor polynomials. That's why we went through the last section, because we're going to try and reduce these into their lowest possible form, simplified rational expressions. So if we look at example 2, we have x squared plus 4x minus 12, and that's going to be divided by 3x minus 6, and it says reduce that. Okay, can it be reduced? Well, obviously it's an example, so likely yes, but let's look at it anyway. So remember here, we were looking for a factor of that. Well, if I look at this, remember in the way that I used to solve it, I noticed that the 12 is made up of 12 and 1, 2 and 6, and 3 and 4. Because the leading coefficient is a 1, that's why this works. and I notice that it's negative. So one of these has to be negative. It can be that side or it can be the other side. So right now I'm just going to look at this guy in particular stands out to me. Why? Because minus 6 plus 2 is 4. So if I switch the negative over to the 2, and I look at 6 and negative 2 as the factors, so I have x plus 6 and x minus 2, right? Then I notice that I get x squared plus 6x minus 2x minus 12. And these two add up to plus 4x. And that is the same as that one there. So I'm going to put that as our factorization. Plus 6x minus 2. Then, at the bottom, I have 3x minus 6. Which, if I factor out a 3 from that, then this guy becomes a 2. And look at that. I have an x minus 2 in the top and an x minus 2 in the bottom, and so my factorization ends up being x plus 6 over 3. There is a tip on the side that says, do not make the mistake of trying to reduce further by dividing terms, because I can divide the 6 by the 3, but then I'd have to divide the x by the 3. Don't forget that. Some people will say, oh, well, that's the same as x plus 2, because I just got rid of 3 to the bottom. That's incorrect. It's the same as x over 3 plus 2, but that's not what you want here. This is in its reduced form, and that's fine. Now note that the original expression, this is cutesy, but note here that this expression here was undefined when x was equal to 2, because it gave us a 0 in the denominator. So this is not equivalent until you say that the domain of this last guy that we get is restricted to all x not equal to 2. It's very pedantic, and only the strictest of teachers will counteroffer it because they are looking for it. But yes, it is mathematically correct. So let's look at a couple of other ones. I'm going to leave that example in there because I'm definitely going to do that one for the slides. Example 3 is reducing rational expressions. A. It says, when simplifying rational expressions, be sure to factor each polynomial completely before concluding that the numerator and denominator have no factors in common. Moreover, changing the sign of a factor may allow further reduction, as we're going to see in part B here. So let's look at this one, x cubed minus 4x over x squared plus x minus 2. If we look at the top, easy, we pull an x out of there and we get x times x squared minus 4, which can be factored even further to x plus 2x minus 2. Okay. Now we look at the bottom, we have x squared plus x minus 2. Well, 2 only has 2 factors, so we know that we're going to have x and a 2 and an x and a 1, and we just have to determine which one it is. The x in this guy is positive, which means that the 2 has to be the greater of the factors, so that x, this 2x will add up with that minus 1x and give us a positive x as a result. So we know that those are the factors, so we come over here, come on, and we have x plus 2 and x minus 1. X plus 2 is going to cancel out, and then we have x times x minus 2 over x minus 1. And remember, this original expression was 0 when we have to carry along, I guess, x is not equal to negative 2. because that information was lost. X cannot be equal to positive 1 either, because that makes the new expression and the old expression equal to 0. However, that information is not lost because we have this here to tell us that the domain is restricted. Let's look at B. We have 12 plus x minus x squared. I don't know why they write it backwards in some cases. 2x squared minus 9x plus 4. The one on the top is backwards, but it's also the leading. I guess they wrote it backwards because the leading coefficient is actually negative 1. So if you factor it out that way, you can look. Come on. Minus x squared plus x plus 12 is going to be the same thing as minus 1 times positive x squared minus x minus 12. So if we can solve this and then distribute the minus 1 through one of the answers, you'll get the answer. So the one that gives us that, as before, is going to be x minus 4, x plus 3. The factors of 12 are 3 and 4. Minus 4 plus 3 is going to result in minus 1. You can't see where I'm pointing, so I have to circle it. Minus 4 plus 3 is going to result in minus 1. So that's what we get here. So that's how we know that's correct. And, I actually wanted that. I have this minus 1 here, which then I can throw in here and have minus x plus 4 times x plus 3. That'll give me this version of it. Same thing. So we'll write that as 4 minus x instead of x minus 4. So that's going to be the top. And in fact, the way he writes it is minus x minus 4, x plus 3. And then on the bottom is a, I'm not going to solve it, I'll just use his, 2x minus 1 times x minus 4. So if you look at that x minus 4, you have to factor out the negative sign to be able to cancel those out. So then you have minus x plus 3 over 2x minus 1. And you can distribute that negative sign if you want to be 3 minus x, or so that's going to be equal to 3 minus x over 2x minus 1, or it's also going to be equal to minus the whole thing of x plus 3 over 2x minus 1. And if you really want to be crazy, you can distribute the negative sign on the bottom, and it's going to be the same thing. X plus 3 over 1 plus 1 minus 2x. Sorry. Okay, so then there are operations with rational expressions. And I'm going to save that for the next stream. Everybody have a good night, and I will be on very soon since I don't like to end in the middle of a chapter. But y'all have a good night. We'll talk to you soon.